Hello and welcome back to the video lecture for Introduction to GPS. The intent of this video lecture is to provide you with a short lecture that's going to highlight key components or concepts pertaining to GPS. Today we're going to talk about how does GPS determine your position. So last week we looked at 2D trilateration. Next we're going to look at this from a 3D perspective. So distance to several satellites are calculated from measurements of the time it takes for radio waves to reach from the satellite, whose positions are precisely known, to the receiver that's being held by you or in your car. So distance is equal to velocity times time. And velocity is the speed of light, which is 186,000 miles per second. And time is measured in seconds. So let's look at an example here. So a signal leaves a satellite at 9:00.00 a.m. Notice we have a lot of decimals there because we're talking in very, very short periods of time here, very short seconds, less than a second. Traveling at 186,000 miles per second. How far is the location, the receiver, from the satellite at 9:00.065 a.m.? So we have a change of time of 0.065 seconds, so not even 1 second. So remember that distance is equal to velocity times time. So for the velocity, we would just put in the speed of light, and the time would be the 0.065. And the answer is 12,108.36 miles away. That is how far away the satellite is from the position that receiver is at. This is just an example of how we calculate this distance from the receiver to the satellite. I'm not expecting you to do any of this math in class or any quizzes or exams if there are any. It's just something that you should understand. So here we talked previously, as I said, kind of about 2D trilateration. Now we're going to look at this from a 3D perspective. So one measurement narrows down our position on the surface of a sphere. So we know that we're somewhere 12,000 miles away, somewhere in this gray area. When we add a second measurement, we can now narrow down our position to a little more. The intersection of two spheres is a circle. Now we know that our position is somewhere on that circle. So we're somewhere in there. We don't know where, we're somewhere, where that black circles in the middle of the diagram are. So adding a third measurement now narrows down our position even further. The three spheres intersect at only 2 points, and we can discard one of the 2 points because it narrows down to the Earth. It's nowhere near. One of those points is not going to be near the Earth. One is going to be on the Earth, one is not going to be. And the computers in the GPS receiver have various techniques for distinguishing the correct point from the incorrect point. So in theory, we should now know where we are on Earth's surface, or our receiver is on Earth's surface. So now we should know, as I said, we should know our X, Y, and Z, or our latitude, longitude, and altitude with this measurement. However, there's a problem, which is called timing offset, that causes error in the measurements. So to solve this problem, we're going to need a fourth measurement to establish an accurate 3D position. And that's why we're going to need 4 satellites at all times, at minimum, to calculate a position. So timing offset refers to the difference in synchronization between the satellite clock and the receiver clock. So the receiver clock uses this accurate quartz clock, but it's not nearly as accurate as these highly accurate satellite clocks. If we had one of these atomic clocks in our receiver, nobody would ever be able to afford a receiver because it would just be far, far too expensive. So they have to use something different. They have to use something that's cheaper, and they use a quartz clock. So this difference causes this timing measurement to be slightly off. So that's why a fourth satellite corrects for clock error. So here we're going to look through this example of 2D timing offset. So in an ideal situation, there would be no timing error. So let's say we're 4 seconds from satellite A and 6 seconds from satellite B. Our position is where the two circles intersect. We can throw out the other position because it's nowhere near the Earth. Remember, in 3D, it takes 3 measurements to get to this point, but we're looking at this from 2D to make it a little bit more easily understandable. So if the receiver clock is 1 second fast, it's ahead 1 second from the satellite clock, the receiver will think the distance from satellite A is 5 seconds and the distance from satellite B is 7 seconds. And it quote-unquote thinks our position is where the two dotted circles intersect. We obviously have an incorrect position here because of timing offset. When the receiver gets a series of measurements that cannot intersect at a single point, it finds the adjustment to all the measurements and lets the range go through one point. So in this example, subtracting 1 second from the 3 measurements makes the circle intersect at this point, highlighted by the yellow circle. Or excuse me, not the yellow circle, the red circle in the middle of the diagram. So timing offset recap. So the first 3 measurements narrow down our position. The 4th measurement is needed to correct for the difference in synchronization between the satellite and the receiver clocks. The satellite uses an atomic clock, very accurate. The receiver clock uses a quartz clock, not nearly as accurate. There's going to be timing differences. It's going to be different. If you look at your watch and I look at my watch, they're not going to be the same. And if you're using that time to calculate distance, they have to be spot on. So 4 measurements, we have 4 variables. We can now calculate the latitude, the longitude, altitude, and timing using timing offset. So that is how and why you need at least 4 satellites to get a fixed position of where that receiver is. Anything less than 4 will not be accurate and will not work. On that note, see you next lecture.